In the previous lectures, we discussed about interpolation. In this lecture, we will discuss another important numerical technique, that is what we call as a numerical integration. So what it means is, why do we need this numerical integration is, you must have realized even from your school days or in your undergraduate days and all, most of the time, most of the functions, you can somehow manage to differentiate. The moment if you want to integrate a function, many times that is almost impossible, because even simple functions are often cannot be integrated analytically. I can give you a simple example. Say for example, sinc function, that is sin x by x. If you try to integrate this function from a to b dx, you can't integrate analytically. Or why go for this? Even your e power minus x square dx, a to b, this also cannot be integrated analytically. And many a times what happens, you don't even get this simple function, you get much complex functions. Maybe the integrand may involve some special functions. So one of the common function what the people when they face when you are studying the synchrotron radiations, all those something is what you call is a k5 by 3 of j dj x to infinity. So these are some integrations. This is your modified Bessel functions of order 5 by 3. So this is a function usually face when you are trying to solve synchrotron emission from a relativistic electron population. So these are all the problem what we face in physics, which we cannot solve it analytically. So, and in these cases, you need to approach numerical methods to provide some answer to these problems, and that's how this numerical integration is very important in the research life. Well, so and this integration we will face it often, because as I told you from the very beginning, most of the physical system, the physical process, what we are seeing in our day-to-day life, they can be described by a differential equation. Often they are second order differential equation, second order partial differential equation. So you bring out lot many approximations, you boil it down to a simple differential equation, ordinary differential equation, and then you struggle to find out an answer. What you finally end up is an integration. And you will struggle to reach up to there, and you will end up in integration, and that integration cannot be solved analytically. So, and this you face it very often. So, one primary thing is, once you get an integration, will I able to get an idea what that integration is, what that integration is when I plot between certain limits, because that's where the answer lies. So, that's why this numerical integration is a very important tool which everyone will be using in your research life. Fine. So now how are we going to do this, perform this integration numerically? This is more or less connected to our earlier lecture on interpolation. So what am I saying is, so we are having an integration. So let us say I equal to say some a to b f of x dx. F of x is some function. So the idea, okay, let me try to plot that function. So what will be like is, so let me plot, this is x, and this is f of x, and let the function be say something like this, whatever the function, or any oscillatory function or something. Fine. And let me put it down. This is our, let me put up, this is a and this is b. This is b. And when we say that we wanted to perform the integration, that means we want to find out the area under the curve. This is what a to b is means. So this is your f of x, and we want to perform the integration. So the idea how we are going to perform this integration numerically is, again, if your function f of x is smooth, we don't know what function it is. It can be any complex, any function, can be a special function, any functions which a lot of complexity involved in it, doesn't matter. If this integrand can be, if you try to plot the integrand, if it is a smoothly varying curve, then any smoothly varying function can be represented by a polynomial of certain a certain degree or maybe infinite, say infinite series you can take it up. So means to extend more accurately, we can describe that function as a polynomial of certain degree, and degree or something. And now if I give you a polynomial and if I ask you to integrate it, integrating a polynomial is trivial. It is very simple. So now instead of I'm integrating the f of x, what I'm going to do, I will convert this integrand into a polynomial which matches my curve and integrate that polynomial. So this is what the technique is being employed in performing an integration numerically. Well, so now saying that, so now how am I going to construct the polynomial? So the first step is, so anyway we know in earlier lectures we saw how to construct a polynomial from a set of points. That's what we saw in an earlier class. So what am I going to do? How I am going to construct the polynomial on this integrand is, let me divide that integrand into finite intervals. So I am going to divide this integrand into some finite intervals, maybe some n or some n intervals I will do. Now, what am I going to do? So now let me see. So if I wanted to construct a polynomial of degree 0, that means a constant line, I can do it. So then what am I going to do? So I will construct a polynomial of degree 0. So that is a constant line, that is this. This will be the polynomial of degree 0, starting from all these points. And then, so I take the polynomial of degree 0 and then try to numerically, then I can integrate this polynomial and keep adding all the one. That's what give me the simple estimation of the integration. But of course, you know, it is not complete, it won't be accurate because you miss all these points and you miss extra points here and all. So this is not accurate. So instead of interpreting this integrand as a polynomial of degree 0, I can use, when it's a degree 0, you need only 1 point. So what am I going to do? Instead of degree 0, let me try to interpolate the function in between the interval as a polynomial of degree 1. Degree 1 is a straight line. Okay, so when it is a straight line, so what am I going to get? I just connect them with a straight line. You can see. So when I interpolate the function in between 2 points at a straight line, so this is going to be better than my earlier estimation. So now if I go further, there's a polynomial of degree 1, that's a straight line. Now if I want to go further accurate, I can go for polynomial of degree 2, which needs 3 points, as we saw in earlier class. So 3 points, so then it makes a smooth curve, and that will be connecting it. So now you can see I keep increasing it. So by that, what we are doing is, by increasing the degree of the polynomial, which is going to interpolate my integrand, collecting certain points, so I can actually get the integration more and more accurate. And this is what the technique employed in our numerical integration technique. Okay, so now if I ask you, so then whatever the polynomial you try to use the polynomial to express the integrand between the certain intervals, so it's not going to be accurate as the actual integration. It's all is going to have a slight deviation from because the area under the curve, so there can be slight deviation from what the exact integration will be. So now if I ask you what should be typically the order of, and what are the factors that accuracy of this integration is going to be depend upon, is first of all the interval width. So the h, if I call h as the interval width, so this width, whether I am going to make it a very narrow width or larger width, that is going to decide. If I make more narrower width, so then my interpolating polynomial is only for a small region of the integrand may be expressed as a polynomial better than when I taking over a larger region. Suppose for example, second order polynomial I am going to do, second degree polynomial. So second degree polynomial I can express over a smaller region more accurately than a larger region. So therefore, the interval width, h is one of an important factor which is going to decide the accuracy of my integration. And not only that, other thing, as I said, this is the one, and other thing is the degree of the polynomial. Whether I am using the polynomial of degree 0 or 1 or 2 or 3, that's also going to decide how accurate am I going to perform my integration. So the accuracy of the integration is going to depend upon two quantities. One is h, another one is the degree of the polynomial. We can call either the degree of the polynomial or certain derivative of the original function. Why? Because it's simple. So for example, your integrand, the differential means the derivative of the integrand will remain for large n. It may not vanish. It may be existing for large n. For example, let us take f of x equal to sin x by x, a simple function. So this derivative exists for any n. You take n, 10, 20, 30, 40, whatever, this derivative is going to be finite. It's not going to make 0. On the other hand, you try to represent this as, from the interpolation, I am going to make it, approximating it as ax square plus bx plus c as a quadratic equation. So a polynomial of degree 2. Now, so this is what I am representing this with f bar of x. Now this polynomial, the derivative of this polynomial goes to 0, the third derivative of it. Or if suppose nth degree polynomial, if I use nth degree polynomial to interpolate the function, n plus 1th derivative is going to become 0. So therefore, either you can call it as a degree of the polynomial but actually for actual function, n plus 1th derivative will be finite. It won't be 0. Since you approximate it as a polynomial, that particular derivative is going to become 0. So alternatively, you can write instead of degree of the polynomial, you can say it as maybe a certain f of n plus 1th derivative of j, where n is a polynomial, a degree what you have used to interpolate the integrand. So this technique is what we call as a, so by this way, when we perform this integration, so and then perform the integration, you will see for different degree of the polynomial, we will get different algorithms, and that's how the algorithms are named under different names. We will see it one by one as we go along. So now the first task is, the primary task is to construct the polynomial, rather say replace this integrand with a polynomial. As I told you, so instead of taking all the points and constructing a polynomial of high order, I can take up a small points, and when I take a small number of points, maybe 2 points, maybe 2 point or 3 point or 4 point, is a small region in the f of x that can be easily represented by a polynomial of a smaller, lesser degree. So instead of taking up a large one, I will divide it into small h intervals and club 1 or 2, 3 points, and then try to construct the polynomial based on 1 or 2, 3 points, and then I repeat the whole thing for all the other rest of the x values starting from a to b. So So we have to develop the algorithm for that. What we are going to do is, so let me take up, so this is from let me take up some value, say for some point I am going to perform integration. Let me call it as x0 to xm. So I will perform, I will try to construct a polynomial, I try to represent the function in between this interval as a polynomial, and then I integrate the polynomial. First step is to construct a polynomial. So what am I going to do? Instead of performing this integration, I am going to perform another integration, I equal to x0 to xm f of x dx, where x0 is less than or equal to a and xm, greater than or equal to a is less than or equal to b. Fine. So now I have taken a small segment of this integrand, and I will derive and get an algorithm, and then I will repeat for all the values. So now, so this integration, let me try to use some change of variable. Okay, so first thing I want to somehow, this x is a continuous quantity, if you know. X is a continuous quantity because f of x dx is a continuous quantity. Somehow I wanted to replace this continuous quantity by with a discrete quantity, that is 0, 1, 2, 3, 4, like that. So then what I am going to do, let me use this. So x, any x can be written as x0 plus h times t. So remember, t is also continuous quantity. The moment when you put t equal to 0, 1, 2, 3, then we get the abscissas. Okay, so for in this representation, t is a continuous quantity. But once we try to discretize this t as 0, 1, 2, 3, 4, then it becomes a abscissas. So let me do this change of variable here. So when your x is equal to, okay, what will be the limit? When x is equal to x0, t0 will be equal to 0, and when x is equal to x sum, so then this will become what? X is x sum equal to x0 plus h and tm. Let us call it as tm, that is the upper limit. So this will be what? So tm will be x m minus x0 by h. Okay, so one discrete, this is nothing but m. Am I right? Yes, because x of m, okay, x of m is what? X of m equal to x0 plus mh, and that's what this is. So when I do the change of variable, this integration I is going to become, okay, so, and yeah, when I do this t, so f of x, so d of x is going to be h dt, so h will come out, this will be 0 to m, and let me call this a function in t, let me call it as f of t dt, where f of t is equivalent to, tell me what is that, f of, what is that, x0 plus ht, that's f of x. Fine. So let me remove this one here. So what we have done is, so our integration we have changed it to 0 to m f of t dt. Okay, so as I told you, now f of t is 0, 1, 2, 3 and all. Instead of writing as f of t, since I know I am going to discretize this t, so instead of f of t, I will write it as f of suffix t. Okay, and now where the t can go from, t is 0, 1, 2, 3 and all. So, and we have to now represent this f of t. We have to represent this f of t as a polynomial in t. If I represent f of t as a polynomial in t, then I can perform this integration, and that's how the numerically I will be able to solve this integration. So how are we going to represent this f of t as a polynomial? We have already seen in the earlier class, one of the simpler methods, we have taken evenly spaced intervals. Of course, we know that you can use a Newton forward difference or even a backward difference to construct the polynomial, and let us use a forward difference. So what we do, we add a forward difference operator, f of I will be equal to f of I plus 1 minus f of I. This is correct, right? Yeah. So then del square f of I will be equal to del f of I plus 1 minus del f of I. So we keep on going like that, and then if you remember what we did is, then I'm not going into that, you can refer back the old lectures how we did it. So what we can do is, so if you want to write f of 1, this will be 1 plus delta f of 0. F of 2 will be 1 plus delta whole square f of 0. So we can do this and say, for example, for us we have f of t. F of t will be 1 plus delta power t f of 0. How we got this? You can go and revise back the old lecture, the previous lectures on interpolating you for an evenly spaced data. There we have shown how we can arrive this. So what we are having is, so let me remove these guys. So then this is f of t. So what we have, so f of t we represented as 1 plus delta to the power of t f0. And what we are going to do now is the same way. What we did, we are going to expand this in binomial series. So that will be what? f0 plus f0, but delta f0 by 1 factorial into t here, right? Yes, plus delta square f0 by 2 factorial into t minus 1 t minus 1 plus delta cube f0 by 3 factorial into t minus 1 t minus 2. So we go similarly up to plus delta power m, because we are having, oops, sorry, we are having only up to m, f0 divided by m factorial t into t minus 1 t minus 2 up to t minus m plus 1. This we saw in our earlier class also. So this is how we got the, so now we can see this is what we want. We had f of t, so the f of t is converted back into a polynomial in t. So now let me substitute this in the integration. So what we are going to have, the integration I, which is equal, which is h times 0 to m, that's the integration. So I forgot to write, I removed that. Zero to m, and f of t, in the place of f of t, I can write this function f0 plus delta f0 by 1 factorial t plus del square f0 by 2 factorial t into t minus 1 plus del cube f0 by 3 factorial t minus 1 t minus 2 on plus mth difference 0 divided by m factorial t into t minus 1 t minus 2 into t minus m plus 1, and the whole thing into dt. Oops, I don't have space, so let me write as dt here. So this is, so finally we got our polynomial which is going to represent the function which is going to represent our integrand, and we will integrate this polynomial, and then we can perform the numerical integration. So what we have done, this integration, we have successfully represented this integration f of x dx, where f of x is some function, whatever, we don't know that. And okay, I removed that f of x. So yeah, where was it first? F of, how the f of x and this are connected, I wrote it there, right? How the f of x and this capital F connected, if you remember, I wrote it earlier. So we had f of t, or f of t is equal to f of t, and that is equal to f of x0 plus ht. This is the way these functions are connected. So then we can actually find out, correct. So now we can find out, given this integrand f of x, we can find out what is my f0. Then you can perform this operation, and we can do this numerical integration. So we are not yet done, because we have not integrated the polynomial till now. So this formula is what basically, the moment if you truncate, so now we can see. So what is going to be a choice of m? What is going to be choice of m is going to decide the degree of the polynomial what you are going to going to consider, interpolate. You try to represent the function within the limit. So so by taking m equal to 1, 2, 3, 0, whatever we found, we can actually construct the polynomial of certain degree, and that polynomial will integrate. So this is what we call as a Newton-Cotes algorithm or whatever. So in fact, this is not Newton-Cotes algorithm. This is the governing function for producing all the Newton-Cotes algorithm. If you have learned, if you are earlier classes, you would have, there are a lot many algorithm names comes. That is trapezoidal, Simpson's, 1/3. There are many other algorithms will come, and Simpson's 3/8. All those things come. This also. This is the basic. We will see how from here, how will you arrive to this algorithm. We will see it shortly. So this is the basic governing integration which we have to perform, and if you perform this integration, we have successfully performed the actual integration numerically. So basically, we have represented the integrand as a polynomial, and we have to perform we have to integrate this polynomial, and once if we integrate this polynomial, then we got the approximate expression for this integration, approximate value for the integration. Fine. So before we go into finding out how to integrate this polynomial, where I am going to truncate all those things, let us try to find out what should be typical error in this Newton-Cotes formula. Okay, fine. So what we are doing is, so if you remember what we did when we are coming from f of x to f of t, we used on how this t. I didn't write that. Actually, we should have. Yeah, it's there. So this is how the x and t are connected. So for example, let us take the integration. What we have, integration of x0 to xm f of x dx. Let me write it as 0 to okay. Let me again use a change of variable. What am I going to do? I am going to use a change of variable where let me write x0, x as x0 plus say some z. So when I do this change of variable, this integration is going to become what this will become? This will be integration of f of x0 plus z dz, and then what will we have when x is equal to x0, z becomes 0, and when x is equal to xm, this will become z upper limit will become xm minus x0, that is nothing but mh. Am I right? Because xm will be equal to x0 plus mh. Okay. So xm minus x0 is going to be mh, so upper limit will become mh. We have to perform this integration. So now let us expand this in Taylor series. So what we are going to get, 0 to mh. So this will be f of x0 plus f prime of x0 divided by 1 factorial into z plus f double prime of x0 into z square divided by 2 factorial, or whatever the way, right? Plus it's go on. So it's an infinite series. So this is what I have done. So let me write it to a certain term, say mth term. So we are truncating a term. So I will write it as f of mth derivative of x0 and z power m divided by m factorial plus there are terms and that into dz. Now if you see, if you try to get an equivalence between this and this, what we have done is, since we have written in a discrete form, we use the binomial series, and this truncates at mth differential. So this is the way where you are truncated. So beyond this, if you see, so if I use this as a polynomial to represent this function, and if I perform it, the next term will goes to 0 because m plus 1th derivative of this polynomial is 0. So that's what the error. But my actual function, the derivative may survive. So by representing this integrand as a polynomial of this polynomial, you can see from here what will be the degree of the polynomial. So, so m plus 1th derivative will goes to 0, and that's what the error I'm going to add in this by approximating the integrand as a polynomial. So let us try to see what will be that factor. So the factor which I missed, so we have what we have done, we have truncated this up to here. So, and this becomes approximate. So by actual integration, so what the term we actually missed is, the term what we missed is the next, I will take the leading term. Because assumption is other terms will basically, leading term is owned as the maximum magnitude term. So that's what matters. So that term is f of m plus 1th derivative at x equal to x0 z power m plus 1 by m plus 1 factorial, and this is whole integration, right? So this is going to be integrated between 0 to m plus h, 0 to m plus mh, sorry, 0 to mh and dz. So this is the term which we actually missed, because that this derivative, by expressing this is a polynomial of degree m, so this is the m plus 1 derivative will become 0, and this is a term we lost by approximating as a polynomial. So let us try to find out what this term will be. Of course, this is not a function of z, this you can take it out. So this will typically go as f of m plus 1 of x0 into z of m plus 2 when I put the limit of 0 to mh. So then we can see, so when I put up, so this typically, I'm not putting the exact number, so this typically goes as f of, or I'll write it here itself. So when I put it z equal to mh, so this I can write it as simply h. This is the order. So typically the error will go in the order of m plus 1 derivative multiplied by the h to the interval width to the power of m plus 2. That's what we, in the beginning also I said. The error is going to depend upon the interval width as well as the derivative, what's the degree of the polynomial you are using to approximate your integrand. So typically, so we want to note it down somewhere else, the error in the Newton-Cotes formula will be, okay, let me maintain it here. So this will be the typical order of error. So let me write it out as this f of m plus 1 x0 h to the power of m plus 2. So this is the typically the order. Okay, yeah, we said that we normally don't write x0, we write it at some value j, because that is a value between a to b or x0 to xm, x0 to xm, where your the derivative m plus 1 derivative is going to be maximum. Okay, not at x0 or particular point. Fine. So that's what we typically do it. And okay, now let us try to derive all the Newton-Cotes formula, what we were studied in our earlier classes, in your undergraduate classes and all. So let us try to derive those formulas. Algorithms we will see. So the first simple algorithm is, let me consider the case for m equal to 1. When m equal to 1, what I am going to do is I am going to represent this polynomial as a polynomial of degree 1. You can clearly say that will be a straight line, and if you remember the name of that algorithm, that's nothing but your trapezoidal rule. So what we are doing in a trapezoidal rule is, let me consider the case m equal to 1. So when m equal to 1, this integration I will become h into 0 to 1, m is 1, 0 to 1. So and this term will be f0 plus I missed something here. Oh, sorry, this t is there. Delta f0 by 1 factorial into t, that's it. With all other nothing terms, because when you put, you can see, when you put m equal to 1 here, it stops at t. So of course, it will be only t. So of course, only these two terms will survive. And so, okay, let us do this integration. Okay, so we want to find out what is delta f0. So if you remember what delta f0 is, let me use this color. So that delta f0 will be equal to f1 minus f0. So let me put it there. So what we are going to have, this will be h into 0 to 1 f0 plus f1 minus f0 into t dt. Okay, so let us do this integration. So h into this is f0 t. So f0 into t, that be what? f0 into t at 1 to 0 plus f1 to f0 t square by 2, and that to 0 to 1, and that's what the integration is. So, and this will become, so your I will be h into, so t is 1, so it is f0. So when you put t equal to 1, so what you are going to get is plus f1 by 2 minus f0 by 2. So this will be h into h by 2 into f1 plus f0, or if you remember what is our f1, f1 is, so when you put f1, this will be x0 plus h, correct? When t is equal to 1, x0 plus h is nothing but x1. So this will be h by 2 into f of x0 plus f of x1. And that's what your trapezoidal rule. So what you have taken, so we have, so this is your x0 and this is x1. So what this formula is nothing but the area of the trapezium. That's why this rule is called as your trapezoidal rule. So okay, good. So this is the way we have performed. So by setting m equal to 1, I have basically performed the integration from x0 to x1. But what we have to do, we have to perform the integration from a to b, or say rather from, I will set this as x0 to some xn. So I have to keep adding all the elements. So then what will happen, so your final integration, this is only for a small segment, that's what we started with. Our actual integration is from a to b. Okay, so the actual integration is what for, let me write it as from x0 to xn. Where will I write it? Okay, fine. So let me write it down here. So the final integration for your integration I, which is equal to x0 to xn, where x0 is your a, b, whatever you call, that is somewhere else there. Okay, n will be f of x dx will be, so I have to basically divide it into small intervals, and each interval. So then if you perform what happens, so what we are going to get is, first term will be, for every term there will be one half term will keep adding. Okay, so what we are going to write is, so this will become h by 2 into f of x0 plus 2 f of x1 plus 2 f of x2 plus 2 f of x3 plus it keep on going plus 2 f of xn minus 1 plus f of xn. So this is what our numerical integration using a polynomial of degree 1, and this method is called as your trapezoidal rule. Okay, cool. And this is what a trapezoidal rule is. So remember, if you have performed only this, that means you have performed only for one small interval. but our aim is to perform the whole integration. So you have to keep adding this plus this plus this plus all the thing you have to add up. So that's what when you add up, so this f0 will come, f1 will come twice. Because f0 plus fx1, next only fx1 plus fx2, so these all will come twice, so that's why written twice. Only the first and the last element will be f of will be single only one time, so that's what this formula you will get it. Fine, so this is what your trapezoidal rule. Yes, of course we can tell what is the typical error will be. Since where m equal to 1, the error will be f double prime of j and h to the power of 3. So this is the typical error in the you get from the trapezoidal rule. Now let us consider for the case m equal to 2. When m equal to 2, what you are going to get, this algorithm what you are going to get is what we call as Simpson's one-third. So this is the algorithm you will get. So now let us concentrate on how to get, how this algorithm will get developed when the case of m equal to 2. So when m equal to 2, this integration I is going to be, I will be integration of h m equal to 2. So this will become 0 to 2. And what we are going to get is f0. So you can see when m equal to 2, you put m equal to 2 here, this stops at t minus 1, that means it stops up to here. Oh, the term will comes up. So we will try to do that. So that's what, when m equal to, this is what the term you will get, plus del f0 by 1 factorial t plus del square f0 by 2 factorial t into t minus 1, and that's it, and then we will have dt. Fine. So what is del f0? f1 minus f0, del square f0 is equal to del f1 minus del f0. So when you put del f1 equal to f4, this del square f0, let us try to do that. So this will be h into integration of 0 to 2 f0 plus del f0 times t plus 1 by 2 times, let us write del f0. Del f0 is f1 minus f0 into t plus, this will be 1 by 2, del square f0 is, okay, so this will be del f1 is f2 minus f1 minus del f0. So minus del f0 is minus f1 minus f0. So this will be what? f2 minus f0 into t into t minus 1 times dt. I am not going to perform this integration. This is trivial. You people can do it in your notes. You can a paper and a pen, take a paper and a pen, do this integration. This is trivial. So this will come out to be, I guess I written this correct. What happens? So del square f0 will be del f1 minus 0. Oops, sorry, I made a mistake. So what this will be, del square f0 will be del f1, that is del f1 equal to f2 minus f1 minus del f0 equal to f1 minus f0. So this will become f2 minus 2 f1 plus f0. Sorry. So this will be what? f2 minus 2 f1 plus f0 into t minus 1 times dt. Okay, so this integration you can do it by yourself. This is a simple integration. So I am just writing down the what is the answer of this, what is the final integration you will get is. So what you get f0 is nothing but, if you remember, our f0 is equal to f of x0 and f1 will be f of x0 plus h, which is f of x1, and f2 will be f of x0 plus 2 times h, that is f of x2. Okay, so we know this value. So therefore, this is what you finally get the integration is h by 3 f of x0 plus 4 times f of x1 plus f of x2. So this is what we call it as a Simpson's one-third formula. So this is when m equal to 2, what you are going to get a Simpson's one-third formula. So this is for the case of, so here what happened, we can clearly see we have, by setting m equal to 2, we have expressed our integral as a polynomial. See, we can remember if t and x are related, okay, that's all, because t and x are correct, t and x are related. That's what we did when we tried to use the so this is what we wrote it as f of x. So t and x are related. So basically, so polynomial, so in x, t will equivalently mean a polynomial in t or x also. So when m equal to 2, we are expressing the integrand as a polynomial of degree 2. Okay, so degree 2 means then we need 3 points. So that's what we get taken 3 points, f0, x1 and x2. So x0, x1, x2, maybe 3 points. So what you do, you take these 3 points, get the integration, then take these 3 points, get the integration, then these points. That way you keep adding, find out the integration from our a to b. So we will not write a to b, so I am going to write it as, say, some, okay, we can call this itself as x0 to xn. So this will be maybe x0 to xn. So when we want to perform, so the integration from x0 to xn f of x will be what? Keep adding it for all the elements. So x0, x1, x2, and that is x0, x1, x2, then x2, x3, x4, then x4, x5, x6. You keep adding these 3 points. So this will become h by 3. So the first one will be f of x0 plus 4 times f of x1 plus f of x2. Now when you add up the next time, another one f of x2 will come. So that makes it 2 times f of x2, and then next term will be 4 times f of x3 plus 2 times f of x4. It keeps on going, okay, until the last terms will be, what will be our last terms? Last terms will be plus 2 times f of xn minus 2 plus 4 times f of xn minus 1 plus f of xn, f of xn. So this is what our final formula for Simpson's one-third integration for is being performed. So let me put it as a box so that we can differentiate from this equation. So this is for the individual segment. Here the segment, we basically club 2 segments and perform this integration. And then when we keep adding all the segments, this is what the formula happens. When we write a program, we write for this, not for this. Okay, we should never write for this one. This is the integration we want to perform. Okay, so now there's one interesting thing with the Simpson's one-third formula. What it is, so let me remove this one. So if I ask you, what is the error in the Simpson's one-third method algorithm? So you would say, of course, we know that error will go of the order of m plus 1 and h per m plus 2. So, so this becomes, when I take m equal to 2, this becomes a third derivative plus m when I put 2 h to the power of 4. But that is wrong. Simpson's one-third is very popular. Why it is popular is its error, the order of error is much smaller than this. Why this comes is I will show you. So that is simple. So if you remember, what we did is, by taking m equal to 2, we stopped with this, right? So we stopped from f of 0, these 3 terms only we had. So suppose the term which we truncated, the next term is what? Del cube f0 by 3 factorial t into t minus 1 t minus 2. So this is the term we truncate up to here. We didn't take the next term. Suppose let us consider, suppose if that term is there, let us assume that term is valid. So if we perform this integration, that's if we perform this integration from 0 to 2. Okay, so and what we'll be having? This will be dt. So what this will be? So what we are to do is, so I'm going to take this term outside. So this will become 0 to 2. There is no t term there. So this is what. I'm not going to do it. You can do it. It's very simple. If you do this, what you will find out is this integration is equal to 0 when you put up the limits. So what it says is, even though, and this will happen only for m equal to 2, you try to do it for m equal to 1 case, that won't be 0. So of course we truncate it, that term will not be 0. This will happen whenever m equal to even. You take it for 2, you take it for 4, you take it for 6, the next term which you omitted, if when you do this integration, that term will become 0. Therefore, what it says is, even though you have performed you have truncated, you have taken m equal to 2, so that means what? When m equal to 2, this is basically a polynomial of degree 2. Since when you perform this integration, since the next term is also becoming 0 by itself because of your integration. So the error, what we said, the error will be the term which is omitted. So automatically the error, since the term goes to 0, the next term will be the one which is going to account for the error. So the error in Simpson's 1/3 will not be the term which this term will be the next term. That means instead of going for m plus 1 and m plus 2, this will be m plus 2 and m plus 3. So therefore, the error in case of Simpson's 1/3, you have to do this, then only you will understand it. If you do it, this becomes 0. Therefore, the next term is going to be 0. So the error will be the next term to that. That's what the error will come up. And that term will be the order of, so for a Simpson's 1/3, your error will be the order of f to the power of what derivative? M equal to 2, but it is equivalent of 3. So it's going to be 4th derivative in xi and m to the power of, h to the power of, so this is m equal to 2, that is equivalent of 3. So 3 plus 2 is equal to 5. So that's why, even though we have taken a considered polynomial of degree 2, this is accurate as if you expressed your polynomial as express your integrand as a polynomial of degree 3, because the next term is going to 0. That's why the Simpson's 1/3 is a very popular and very commonly used algorithm. Okay, so this is what Simpson's 1/3 is, and then we will go for the last one, which I will just quickly, because the same thing, we have to keep repeating it. So now what I am going to do, so let us take as m equal to 3. When m equal to 3, what you get, the algorithm is called as Simpson 3/8. Okay, so I am not going to do this integration, you can do it the same step. So the same step. So when m equal to 3, what happens? So in that case, your integration I will be h 0 to 3, m equal to 3. So f0 plus delta f0 by 1 factorial into t plus del square f0 by 2 factorial into t minus 1, plus it stops in the next term, because when m equal to 3, you can see it goes with t up to t minus 2. So this will become del cube f0 by 3 factorial t into t minus 1 t minus 2, and that into dt. So we can perform this integration. So I'll straight away write down the integration. Now you know how to, the same way you can proceed with your forward difference operator, get those values, and if you perform, So which is trivial. The same way what you have done earlier, you have to do it. I'm not going to do this. Rather, I'll write down the answer straight away. 3h by 8. Okay. Anyway, I can't do, the space is not sufficient for me to do here. F of x0 plus 3 times f of x1 plus 3 times f of x2 plus f of x3. This is what you will get. You can see, you take 4 points now. Okay, so when you take 4 points, you take the 4 points and perform this integration, and this is what your Simpson 3 by 8. And again, so it takes how many points? x0, x1, x2, x3. So x0, x1, x2, x3, 4 points. So you do this one, then take for the next 4, then take for the next 4, you keep adding. So to get the whole integration. So then what happens if you keep adding it? So you can straight away write from here itself. So for your actual integration I, which is x0 to xn, f of x dx will be 3h by 8. So first term will be as it is, f of x0, second term also will be 3 f of x1 plus 3 f of x2, and now this is x3, that is x3 term, 0, 1, 2, 1, 2, 3. So this one. So for the next integration, this term will come up. That's our f0 term. This is lag term. So this is going to become 2 f of x3, and you can keep on doing it out and get whatever the values. So only thing we have to be caution in when you are performing the Simpson's 1/3 and Simpson 3 by 8 is most of the times people don't do it. It works fantastic. It's not serious problem. But ideally, you are supposed to divide your integrand. The interval should be accordingly, you should be able to club it as a 4 points. Here it's okay. When the Simpson's 1/3, we club basically 3 points. You have to divide accordingly, so it will be a multiple of 3. Okay, so that's the correct way of performing your Simpson's 1/3. But most of the cases it works. People arbitrarily take divide the integrand into arbitrary intervals. Still it will work. So to be exact, to correct implementation, you have to remember that. And yes, for m equal to 3, of course, the order of error will come out to be same. You will see for m equal to 3 also, you take out the next term, that won't vanish. So that will happen only for m equal to 2. That's for all the even numbers. For all the even numbers, even though you performed your polynomial of certain degree, but still it will always go for 1 degree higher than that. That's how this numerical integration is being done, using by approximating the integrand as a polynomial. Fine. So with that, I will stop today's lecture on numerical integration. And well, this is one of the, though this is a very interesting method, and we can use this to find a polynomial and do that, but still there is some handicap I am having, because the point is, because I have to divide this into equal intervals. The h has to be defined, means how much intervals I will do, and I am going to make it evenly spaced. Now if I ask you a question, I am not going to make the intervals evenly spaced. Rather, I will find out the value of the functions at certain x values, which are not evenly spaced. They will be unevenly spaced. But I will perform the calculation of the function at certain x values and use that to perform this integration. So what, in other words, what you mean is, you are actually, now what happened, we are fixing up this h value and trying out all this constant 3h by 8 and all those things. If you allow it to vary somehow, the h I am not going to fix. How we are going to vary, we will see it. So I am not going to have fixed h, I am going to find out my abscissas at certain pre-decided values. And is there any way by doing that I can get a better, I can represent the integrand as a polynomial of higher order? So then that is the more superior algorithm. Okay, and that's what algorithm, when we discuss about such algorithm, that's what we call as a quadratures, which we'll see it in the next lecture. Thank you.